in order to understand how these transitions takes place and how to find out the wavelength or the frequencies associated with these transitions. The numerical is find the wavelength associated with the second line of Parston series in the helium ion. Parston series, the third series. We know for this series, the ground state, the electrons comes back to the third orbit or third shell. So remember, in Parston series, the first line in any series is due to the transition from its very next orbit. Like for the first line for the Lyman series is from the transition from second to first. Second line in Lyman series will be the transition from the next level, that is from the third to first. If we have similarly the first line in case of Balmer series, it will be due to the transition from 3 to 2, because Balmer series for the second orbit and the first transition is from the very next one, which is 3 to 2. Similarly, in case of Parston series, the first line will be due to the transition from 4 to 3, whereas the second line will be due to 5 to 3. That is how we have Lyman, Balmer, Parston. So we are talking about Parston series in which we have transition from 5 to 3. So in this numerical, your N1 is 3 and your N2 is 5. This is how you will interpret out from these number of lines. Similarly, the last line in any series is due to the transition from infinity to that particular orbit number. Like the last line in case of Lyman series is from the transition from infinity to the first orbit. Last line in case of Balmer series is from the transition from infinity to the second orbit. So this is how we have got N1 and N2. We know it is helium ion, so your Z will be 2, and we have to find out the wavelength. We know the formula. The formula is the wave number is 109,677, the Rydberg's constant, 1 upon N1 square minus 1 upon N2 square, and Z square we have at the end of this. So we will use these values in order to find out, whenever we will put these values, we can find out the answers in this. Now let us put the values here. 109,677, which is the Rydberg's constant, upon 1 upon 3 square minus 1 upon 5 square, and we have atomic number of helium 2, so it's 2 square. So it is 109,677. It will be 25 minus 9. Here 9 into 25 into 4. Then when we solve this, what we get is that wave number comes out to be 3.1 into 10 to the power 4 per centimeter. Therefore, the wavelength which will be the inverse of this will be 1 upon 3.1 into 10 to the power 4 will come out to be 3.2 into 10 to the power minus 5 centimeters. So this is how we can find out the wave number or the wavelength associated with any of the transitions.